including James Hall, it's like Tian Li were former graduate students of mine. It's like Harris is a longtime collaborator, Jing Zhang is a professor at the University of Michigan. And very generously funded by the National Science Foundation and more recently by the Air Force. Okay, so so what I would like to motivate for you is the following. So it's like in many physical, it's like in engineering problems, you have systems, it's like which have information and physical layers, and there's a tendency to view these things as hybrid systems where the information processing layer is in discrete time, and the physical dynamics is somehow described in continuous time. Because of this dichotomy between the discrete time versus continuous time formulations, one typically attempts to optimize these problems in a sequential fashion as opposed to doing it concurrently. And this is reasonable. It's like when there's a separation of timescales, if you will, it's like between the physics and the information processing layers. But I'm going to suggest certain applications. It's like where that separation of timescales assumption is no longer valid, and that then naturally leads to the question of how you go about thinking about learning in some sort of continuous time setting. Okay, so what we're going to do, the way we're going to approach this is by essentially relating information geometry and discrete mechanics, applying some sort of back error analysis, and then you want to realize machine learning as, in essence, time h flow. It's like a dynamical system in space of probability densities, which then gives you a way of treating it's like information mechanical systems in a unified fashion. So let me give you some motivation for this. So there's been a lot of interest. It's like in recent years, it's like of having really, really small drones. It's like which would then be deployed in buildings. It's like they're meant to basically do reconnaissance. It's like inside buildings. And one of the problems it's like with these drones are that they're very easy to disable just by throwing a blanket at them. So this is true even of the bigger drones, not just the small handheld ones. And so you have to fly pretty fast in order to avoid that kind of attack. So you fly of the order of about 10 meters per second, it's like, which corresponds to about 22.5 miles per hour. And this drone in the middle is capable of flying up to 45 miles per hour, so it's really twice as fast as that. So that's not atypical. And the main point then is that what happens when these drones are flying through buildings, flying past open doors, is that new information is coming to them at a speed which basically violates the separation of timescales assumption. So it's no longer reasonable to have an information processing layer which says that, well, I want my drone to fly in a certain direction. It's like to seek out new information, and then assume that the drone's capable of physically realizing that without certain constraints and things like that. And there's of course also a lot of interest. It's like in the U.S. military, it's like them deploying really swarms of drones. And again, the question is whether or not these kind of swarms of drones might, whether it can be better, it's like described again in sort of continuous time as opposed to discrete time. In particular, because there's a certain asynchronarity to them. It's like when you have a large number of drones, it's like you no longer want all of them. It's like to be marching in time, sort of lockstep with each other, right? So you don't want to have a uniform time step. It's like it's much better to have a continuous time population. It's like to deal with these things. Okay. So the way we're going to approach this is we're going to sort of try to bring together three different things. One of which is information geometry, which is the use of differential geometric tools to describe the manifold of probability density functions. And in particular, the basic idea behind this is that if you want to do learning, it's oftentimes the case that you can think of learning problems as being some sort of optimization problem over the space of probability densities. And if you were to do this, it's like in a traditional way, it's like then what would happen is that you would use the coordinate charts, it's like on the manifold of parametrized families of probability distributions to do the optimization routine, say your Newton method or your gradient descent method. But the space of probability densities is endowed with a natural metric, and oftentimes it's much better, it's like to have, it's like your optimization techniques, it's like respect that underlying metric as opposed to the sort of the ambient metric in the parameters. Okay, so it allows you basically to investigate the intrinsic properties of these statistical models as opposed to their parametric representations. And then as it turns out, it's like geometric concepts like some notion of metric, connections and curvature, then have some connections to statistical issues like, for example, asymptotic efficiency of maximum likelihood estimators. So the more curved the space sort of models you have are, it's like the harder it is. It's like to have sort of good approximation. It's not so surprising. So, and as I mentioned before, it's like many machine learning algorithms can be viewed abstractly as an optimization problem. Okay, and the way you measure it's like the goodness of fit, if you will, it's like is through things like divergence and contrast functions, which are asymmetric analogs of distance functions, and they provide a unified way of measuring information, energy, entropy. And then from these divergence functions, you get induced metrics and connections on the space of probability distributions, and then these differential geometric structures naturally lead to natural optimization algorithms and sense optimization of manifolds. And then what I primarily work on is in discrete mechanics, and discrete mechanics is sort of a way to construct geometric structure preserving discretizations of analytical mechanical systems, primarily Lagrangian Hamiltonian mechanics. And the usual way we do this is through discrete versions of variation principles. And the connection that's like between discrete mechanics and information geometry is that the divergence function, which is information geometry, has an interpretation as a discrete Lagrangian, which is a generating function of a symplectic map. And so we'll see it's like along the way, it's like many different connections. It's like between this and that many of the problems, it's like which one will see have a mechanical interpretation. And the goal, of course, is to establish this connection so that we can leverage the techniques we've developed, it's like for computational mechanics. So as I said, this gives you a mechanical interpretation of certain machine learning algorithms, and then hopefully that allows you to view such algorithms as time H flows in continuous mechanical systems. All right, so what is a divergence function? So a divergence function is a map that takes two copies of this manifold M to sort of some non-negative number satisfying a bunch of properties. Okay, and you can view them basically as pseudo-distance functions, which are non-negative, which take non-negative values, but they don't need to be symmetric in the slots.
Can you explain what these subscripts mean?
Yes. So the subscript denotes a partial derivative, and there's a comma here because there's a partial derivative with respect to the first or the second slot. Yeah. So I guess it's written here, right? So dI is the partial derivative with respect to the I component of the first thing versus the I component.
So did the XX mean on the diagonal? Evaluate it on the diagonal?
Yeah. So you evaluate that on the diagonal. So you take the partial derivatives and you restrict it. So there's certain compatibility conditions. All right, and then from this divergence function, it's like you can get sort of certain sort of differential geometric objects. You can get a Riemannian metric, and you can get these pair of torsion-free dual connections. So you have a metric given by sort of the mixed partials, if you will. It's like validated along the diagonal, and then you have these two pairs of dual connections, and these connections are torsion-free, and they dual with respect to this metric Gij, which is given here in the following sense. So if you think of these as affine connections and the pi's as being the associated parallel transport operator, then what happens is that if you take the inner product with respect to this metric of two vectors, then the parallel transported vectors, but with different parallel transports pi and pi star,
So is it clear from all this that, that everything is going to transform appropriately under change of coordinates to be this kind of tensor field?
So in order to make which a tensor?
Well, so I mean, you've got some coordinate chart on
Sure.
the manifold, but you could
Yes.
always change coordinate charts.
Yeah, so
is
these
it
are,
clear that everything's going to be in a
yeah,
very
everything is
change
well
of chart?
defined, yeah, right, so yeah, they transform the way you expect them to transform. Yeah, so, and so in particular, then it's like you can think of these pair of connections as coming from, as being related to the Levi-Civita connection and some symmetric covariant tensor, which is called the skewness tensor. Okay? so this thing here is the Levi-Cheever connection associated with the metric G, which comes from taking this mixed partial and evaluating it along the diagonal. And then there's this symmetric covariance here. So you can write down the pair of dual connections in terms of these other more fundamental objects. And then as an example of a divergence function, there are these class of divergence functions called Bregman divergences. And they are defined in terms of some strictly convex functional and given in the following way. So you might not have heard of Bregman divergences, but it turns out that they're related to things which are perhaps more familiar. So if that convex function is chosen to be the negative Shannon entropy, like so, then the Bregman divergence associated with this convex function is the Kullback-Leibler divergence or KL divergence. And the metric associated with KL divergence is the Fisher-Brown metric. So that sort of covers perhaps more familiar objects. So that's a sort of quick review of information geometry. Now let me say a little bit about discrete mechanics, and then I'll try to sort of connect the two together. So geometric integrators are a class of numerical methods which preserve geometric properties such as elasticity, momentum maps, B-group homogeneous space structures of the dynamical systems being simulated, and they tend to result in better numerical simulations in the sense that they oftentimes give you better long-term numerical stability and better qualitative agreement with the exact problem. So the way we try to do this is to discretize Hamilton's principle. So Hamilton's principle states that if you have an initial point and a final point, then the trajectory which joins those two endpoints is that which extremises the action integral, which is the integral of kinetic minus potential energy. And one way to approximate this is to replace that trajectory with a bunch of sample points along the manifold, and you want to approximate a piece of the action integral, if you will, through what we call discrete Lagrangian. So discrete Lagrangian depends on a pair of points, Q0 and Q1. So imagine that this thing is approximating an action integral over a short segment, and the Q0 and Q1s are the boundary conditions. And it's supposed to approximate what is called the exact discrete Lagrangian. It's action evaluated along some curve, which is the solution to the Euler-Lagrange boundary value problem. So it satisfies the Euler-Lagrange equations, and it's compatible with the boundary conditions which I prescribed at the endpoints of Q0 and Q1. Of course, this exact discrete Lagrangian is not really computable, because in order to compute it, you need to be able to solve the Euler-Lagrange equations. If you want to solve the Euler-Lagrange equations, you should just stop there and not walk around. But nevertheless, it's like such a solution formally exists, and it's really related to Jacobi's solution of the Hamilton-Jacobi equation. And the existence of this then allows us to construct systematic approximations of the corresponding flow maps. Okay. So in any case, what you do given one of these discrete Lagrangians is that you construct a discrete action sum, which is the sum of these LDs. It's like over a pair of points, and you want that this action sum is stationary with respect to variations in those internal points which I had before. So I fix Q0 and Qn and allow the internal points Q1 to Qn minus 1 to vary, and I want to vary those internal points so as to extremize this action sum. Okay? And when you write down the stationarity conditions for this, you get what I call the discrete Lagrange equations, which are given here. And the D1 means a partial derivative with respect to the first slot, which is Qk, and here this D2LD is partial derivative with respect to the term in the second slot, which is again Qk. So this becomes then a occurrence relationship which tells you, given a pair of points Qk minus 1 and Qk, it tells you what essentially Qk and Qk plus 1 is going to be. And it's easy to see that this map is symplectic, because if you add in momentum variables here, it's like that this is really nothing more than the characterization of a symplectic map in terms of type 1 generated functions, and the Lagrangian, discrete Lagrangian is a type 1 generated function of a symplectic map. So you can apply this to many problems. It's like you can apply this to various articulated rigid body type systems. It's like this is just a double spherical pendulum. This is an articulated rigid body in a perfect fluid. You can add mass effects. These are rigid bodies with elastic tether. It's like so these are models for tethered spacecraft and maybe tethered drones and things along those lines. You can apply them to biomechanical simulations. So this is due to Todd Murphy at Northwestern. He's applied them to modeling human prosthetics, sort of in collaboration with the Rehabilitation Institute of Chicago. You can use this to model marionettes, which are really these big wooden puppets. You can extend them to PDE problems, so elasticity and plasticity problems. This is due to Green's
Can I ask a simple question?
Sure.
So let's just take the double pendulum as
Sure.
a discrete system with a Lagrangian. When you write down the equations, you would only have an initial condition. So then why endpoint condition? So I always make that notion. Well, the endpoint condition is the initial condition of the time reversible system. So that's all you need.
Well, so yeah, this is
So
a
how do you
problem.
interpret
Yeah,
it?
so you don't really have to interpret it because I mean that's just the way. That's just a property of the system, right? But
Sure.
you end up getting a initial value problem at the end of the day. All Lagrange equations are perfectly.
Sure.
Yeah. So it's just you should think of it as a minimization or extremization problem. So perhaps there's a nicer interpretation in terms of quantum mechanics.
So I'm missing where, you get a step that actually allows you to apply this, because you were still having the Lagrangian
Sure.
be exact.
Yeah.
But then,
So
you can only do that if
I'll
if
talk
you know
about how to
the solution.
construct those things.
Okay.
Yeah,
Right.
So it should approximate the exact discrete Lagrangian.
Okay,
But
all right, so there's an approximation
Yeah, it's an
somewhere, but you haven't
approximation
told us
somewhere,
yet.
Right, but
Okay.
I'll talk
Got
about
it.
how to construct that approximation in a computable fashion. Yeah. But yeah, so if you see going from here to here, it's like here at LD without the exact, and here at the LD exact. So all these things are respect to this discrete Lagrangian, which I haven't told you how to construct. Yeah. So, but yeah, I mean, it's like Hamilton's principle is just used to derive the equations in a sort of coordinate independent fashion. But you don't need to know the terminal end state in order to use it the best. Okay, so anyway, it's so let me say a little bit about why it is that you might want to construct numerical methods in this way. There's sort of two main motivations, one of which is its connection with what is known as Noether's theorem. And Noether's theorem basically gives you a relationship between symmetries of problem and conservation equals. And there's a discrete analog of that. So if your discrete Lagrangian is infinitesimally G invariant under the diagonal group action, which basically means that if you have these pair of points Q0 and Q1, and you say you rotate both of them by the same rotation matrix, and the discrete Lagrangian stays invariant under that, then there's an associated momentum map to that, which is preserved by the field. Okay, so that's analogous to what happens in a continuous, mechanical system. It's like where if you have a mechanical system which is invariant under the lifted action of same rotations, then there is angular momentum which is preserved by. And the other thing has to do with error analysis. So we said that it was this exact discrete Lagrangian which you can't compute, but nevertheless generates the exact flow of the all Lagrange equations. So there's a sense in which at least it's like that in this category of discrete Lagrangians, there is an object which then generates the exact solution which you're trying to approximate. So you can ask the following question: if your computable discrete Lagrangian approximates the exact discrete Lagrangian to a certain order of accuracy in the time step, does that give you a numerical method that's like with the same approximation properties? And it turns out that it does. If you have a computable discrete Lagrangian which is of order R in the following sense, then the discrete all Lagrange equations yield an order R accurate symplectic interval. Okay. So now we get to the point of how you actually construct one of these things. Okay, so I'm going to slightly recharacterize the exact discrete Lagrangian. So I'm going to say that the exact discrete Lagrangian is given by this extremization problem. So we want to take the action along some trajectory, and you want to extremize this over the class of trajectories which are sufficiently differentiable and which satisfy the boundary conditions. Okay. And this leads to, and then once you have this, you can talk about how you go about discretizing it. And the way you discretize this is to replace the space of twice differentiable curves with some finite dimensional function space. So this is going from infinite dimensional space to finite dimensional space, and you replace the integral by some quadrature form. And once you have this, then this gives you a computable discrete Lagrangian. So now it's like the question is the following. I said I had this variational error analysis, and I said that if my computable discrete Lagrangian approximates the exact discrete Lagrangian to some order of accuracy, right, then I knew distance. So the question then is, how do these two choices relate to that question of order accuracy? Okay. So before I do that, let me sort of address the group invariant part, right? So there were two pieces, one of which was the no fit here. So how do I go about constructing a discrete Lagrangian which is G invariant? The way you do this is that you choose function spaces which are group equivariant. So what I mean by that is that if you imagine your function space takes a set of data or points and then gives you a curve which is parameterized by that, and you take that data point and you rotate all of them, and you get a new curve. It's like which is associated. And the old curve has to be related to the new curve by that same group action. And if it is, then we see that those interpolatory functions, or the finite dimensional function space, is group equivariant. And if you use these group equivariant function spaces to construct your discrete Lagrangian, then the original continuous Lagrangian is G invariant under this tangent limited action, then you'll get a discrete Lagrangian which is group invariant. And as a consequence, it will preserve sort of these momentum maps which we talked about before. So in the ODE setting, this is not so difficult to do. In the PD setting, this is a little bit more involved. It's like when we have a class of methods for problems which involve, which take values in symmetric spaces. Okay. So the second issue is this accuracy issue. And you've chosen a finite dimensional function space, so it's very natural to ask if the error you get in your numerical solution is related to what is known as the best approximation error. So if you have your continuous solution of a differential equation, you have some choice of finite dimensional function space. What is the nearest point, if you will? It's like, on this finite dimensional function space, it's like which approximates the exact solution with respect to a certain norm. Okay, so that's what's called the best approximation error. And you want that the numerical solution you have is the error is bounded by some multiple of this best approximation error. And if you can do that, then you're in business, because that translates the problem of constructing good approximations to an approximation theoretic question, where now you just have to find good approximation spaces. Right? So what makes this a little bit challenging is that our discrete Lagrangian is defined in terms of this variational problem. So what you're really trying to do is something having to do with what is known as gamma convergence. So you have a sequence of approximating functionals, or approximating it's like minimization or extremization problems, and there's a limiting extremization problem, which is the one which is used to define the exact discrete Lagrangian, right? And there's a precise sense in which the variational problems converge. It's like to that limiting variational problem. But you want to prove that the extremizers of those sequence of variational problems is convergent. So this is precisely what is known as gamma convergence, the calculus of variations. And not only do you need to show that it gamma converges, but you need to show that the rate of gamma convergence is related to this best approximation error. Okay? So it turns out that you can do this, and it requires you to refine this gamma convergence result of Michael Ortiz and Stefan Mueller, which proved that variational integrators converge, gamma converge. And by refining this and then being careful about what the errors you introduce are, you can show that these Reed's variational integrators are order optimal, and they are spectral analogs on geometric. So again, what that does for you is that it reduces the problem of constructing good variational integrators to a question of finding good approximation spaces for where your solution lives. So if you know something about the regularity properties of your solutions, then you can use it's like approximation theory to tell you what are the best spaces to approximate those solutions. Okay, so when you apply this to it's like to polynomial, it's like polynomials of fixed degree, it's like you will have the usual weighted conversions you expect. And if you fix the time step and you increase the polynomial order using these Cherenkov polynomials, then you'll see that they converge geometrically as you would expect. So there are two plots here with two lines, and what that's meant to illustrate is that the error analysis which I presented speaks primarily to the question of what happens to the solutions at multiples of the time step. Okay, so I'm just sampling it's like the solution multiples of the time step, and I'm looking at how those things converge. It's like, but what you can also ask is the following, because when I constructed this discrete Lagrangian, I picked a distinguished element of the finite dimensional function space, which I then used to evaluate this value of the discrete Lagrangian. But you can ask whether that distinguished element of the finite dimensional function space is a good approximation of the continuous solution in an L infinity sense. And it turns out that it is. And if you look at the L infinity error of this distinguished element as a continuous, piecewise continuous approximation of the solution, it converges at half the rate geometrically. And so you'll see that there's this crosses, it's like it have to do with this L-infinity error of the continuous approximant, and it converges in half. So what are the implications of this? The implications are the following. If you apply this to, say, the n-body approximation of the solar system, so this thing on the left is the JPL form ephemeris, and the thing on the right is the mathematical equivalent of the spherical cow, right? So this is the 4 or 5 body, or 5 body. Okay, so anyway, so this is the n-body approximation. It's like this much more complicated thing. And what's noticeable about this is that it's one of these spectral discretizations with a time step of 100 days. So this time step of 100 days is larger than the fastest orbital period, which is represented in the problem, which is that of Mercury. Mercury is an orbital period of 88 days, taking a time step which is larger than that orbital period. And I don't get absolute garbage, and the reason I'm not getting absolute garbage is because when you have 25 Chebyshev, it's like polynomials, it's the approximation power of that space is strong enough basically to capture it's like the full dynamics. Okay? So that allows you to create extremely large time steps. And that's more or less it's like what this sort of second curve is telling you, that they are good, the actual continuous objects are good approximations of the solutions themselves. This is perhaps more clearly illustrated in this plot here. This is a plot of the 3D pendulum. The black dots tell you again what are the discrete samples of the solutions and multiples of the time step, and the thin lines are the interpolating curves, it's like which you obtain from the variation limits. You see again they do really quite a good job of fitting the dynamics. And this is despite the fact that some of them involve rotations which are which involve angles of almost it's like pi, which is sort of the limits of the coordination. Okay, so when you apply this to the free rigid body, it's like they have, it's like the free rigid body has two invariants. It's like one of which is energy, which corresponds to an ellipsoidal level set of corresponds to ellipsoids of different radii, and then you're also on the what's known as the angular momentum sphere, which corresponds to the conservation of the spatial angular momentum, where the body angular momentum representation, which means that the magnitude of the body angular momentum is constant. So you intersect spheres with ellipsoids, and then you get these kind of curves here, and they sort of uniquely determine the trajectories of the free rigid body. If you use explicit Euler in this, it's like you'll see that it violates it's like the conservation properties which you're hoping for. If you use ODE45, it's like have very, very tight tolerances. It does a better job, but nevertheless, it still slowly drifts off these constraint manifolds. And if you use one variant of these variational integrators, which also respects the group structure of free rigid body dynamics, you'll see that it does extraordinary.
Can I ask a quick question about those Chebyshev integrators on the previous slide?
Yes.
So if you do this process of taking approximating polynomials and applying quadrature, you can show that what you get is partition Runge-Kutta method.
Sure.
Is this a known family, partition Runge-Kutta methods?
With the Chebyshev stuff?
Yeah.
It should just be partition Runge-Kutta method, but the main result is the error analysis. It shows that it geometrically converges. Because the function spaces are the same, right? Yeah, so it's
When you do the quadrature, there is some choice there.
yes,
And it might be a slightly different method.
sure, that's true.
Is there like a known family?
I think you just
use
use
of collocation methods where you use the Chebyshev
Yeah.
methods?
Yeah, I don't know.
Yeah, right. But I think it's like the quadrature rule. It's like we had there was just what you get with the Newton codes methods.
Fair quadrature?
Yeah.
Fair quadrature.
It's just the Newton codes methods associated with the function spaces.
So for the inner solar system problem, I mean, in principle, although it doesn't actually happen in the inner solar system, you could have two planets bumping into each other,
Sure.
and the solution is singular. So
Right.
how do you get to bound the error?
Um, Yeah, well, we don't deal with that. It's because usually it's like whenever you do error analysis of a system of these, there's an assumption that the vector field doesn't diverge, and so that's an assumption which is built into the error analysis. You can't really get around if you actually have a collision, then the vector field's divergence, I can then point that something, basically.
But
There are regularizations of this, I mean, it's like, but that's sort of a different beast.
right, but but it follows from that, if the two planets get arbitrarily close,
Sure.
those will be, will depend,
Right, yeah, so
arbitrarily,
what
heavily
if-
on the initial conditions. So
Right.
I'm still not quite sure how you bound the error in this case.
Well, the error is always bounded in terms of something like the Lipschitz constant, it's like the vector field, right?
Okay,
So.
all right, so you would get a very big Lipschitz
Yeah,
constant.
so,
in that
I
case.
mean, there will be constant, I mean, it's like, well, as I said, there's a big O thing, but the big O has a
Yeah.
constant, and the constant depends on the Lipschitz constant. That's just sort of typical. We don't do miracles, right? I mean, the solution's no longer well-defined, and the solution's not well-defined. No amount of numerics, it's like, it's going to help you get out of that.
Yeah.
Right. So, okay, so anyway, so that's sort of, again, a quick review of variational integrators and sort of what, how to construct them. It's like, what are some of the nice properties now? Let me sort of tie it back to the thing I was talking about, which was machine learning. It's like information geometry. So, all right, so this is a result it's like due to Jin Zhang, it's like and myself, and it basically says that if you look at the induced metric, which comes from a given divergence function, right? You can ask yourself, it's like, how well is the geodesic flow associated with that induced metric approximated by thinking of the divergence function as a generating function of a symplectic map. Okay, so you have a divergence function that depends on two copies of the manifold. It looks like one of these type 1 generating functions. You can just go ahead and try and see what happens. Okay, so, and it turns out that it's a reasonable approximation. So it's always consistent. So what that means is that if you take this divergence function and you think of this as a generator of a symplectic map, it's always a consistent discretization of the geodesic flow associated with this induced metric coming from the divergence. And if it is, if this divergence function is a Bregman divergence for some strictly convex function, then it turns out that it's going to be a second order approximation.
What's the, how do I interpret the geodesics in this information geometry?
So,
Probabilistic interpretation.
yeah, that's a good question.
So is this just like, so if you were in Euclidean space and you had a free particle,
Right.
you'd have, your kinetic energy would be like 1 over h times q of h minus q of 0 norm squared. Is this
Yeah.
just like a version of that?
Yeah, so yeah, if you're in Euclidean space, it's like there's a very natural, it's like divergence function, which is just associated.
So it's just norm squared distance.
Yeah.
And this is the generalization of that too.
Right. Well, it's also no longer a distance, right? It's no longer necessarily a distance. It's very symmetric. So anyhow, so yeah, so you can show basically that you get something which is second order accurate. It's like, and the proof is sort of relatively straightforward. You sort of write down formally, it's like in a Taylor expansion, what the discrete Lagrange, exactly Lagrange should look like for the geodesic flow. All right, and then you can sort of start with properties of the divergence function, and you again Taylor expand like crazy, and use all the various identifications you're going to do with the mixed partials. And then you sort of compare it to it. I mean, so this is sort of maybe numerical analysis, and comparing it's like the sort of things term by term. It's like leads you to the conclusion that you need these conditions in order for the discrete Lagrangian to be second order accurate. Okay? And then these are exactly the conditions for the information manifold being Hessian and dually flat, and then that's also a condition which is related to this divergence function being the regular divergence. All right, so that's sort of one direction that's like you can work with. Then the other direction it's like is that if you have a divergence function, well, the other question is how will you construct a divergence function which gives you a prescribed choice of metric and connection? Such divergence functions are called canonical divergences. And one way you can use a mechanical sort of interpretation of all of this is to basically use Hamilton-Jacobi theory for the folding Lagrangian. So I have a Lagrangian which depends again on the metric, which I'm given, and this T, which is the skewness tensor, if you recall. So the skewness tensor is related to, it's really the, up to a constant, it's the difference between the two dual connections, right? And so this gives you a Lagrangian. And then, you know, when I say Hamilton-Jacobi theory, all I'm really saying is that one Jacobi solution of the Hamilton-Jacobi equation, which is of course related to variational integrators, because that's a basic thing that you're trying to construct whenever you're given a Lagrangian system. So you basically just use you know, standard techniques now from variational integration to construct at least a second order accurate approximation. And second order is necessary in order to recover the metric and the connection, and then anything else above that, it's like is great. Right? If you just care about recovering the metric and the connection, that's enough for you. Okay, so so I spent a lot of time talking about geodesics. It's like respect to metrics which are induced by divergence functions. No way have I really connected it then back with learning. And the way you've noticed, you should have noticed that is because I have not yet talked about data. So how do you incorporate data into the problem? How do you incorporate measurements into the problem? So so again, the intuition that's like behind, it's like how one might formulate machine learning in this context is that you have a sequence of estimators which model, if you will, your understanding of reality, and then you have measurements which tie you to reality. And you would like to, you know, minimize the mismatch that's like between your estimator and its predictions of reality. Okay? So if you think of the xi's as these sequence of model distributions which reflect your estimators, and yi's as the data in some sense generated from this unknown real distribution that you care about, then you want to measure the mismatch between these two things. And the way you do this is by applying this divergence function to this pair of points xi and yi. So this is in some sense a measure of the discrepancy between your estimator and reality. Okay, and then the second thing you want to do is that you would like to, in the absence of any mismatch with reality, you would like the estimator to evolve in a nice, relatively smooth fashion. And the way you typically do this in a mechanical setting is you give it some mass, you give it some inertia. Okay, so so there is this term here which, in some sense, if you will, penalizes the mismatch between a sequence of estimators. Okay, so this is morally a kinetic energy-like term, and then this term here is morally a potential energy-like term. Okay? So so once you have this discrete Lagrangian, then you can, in principle, rely on sort of these newly developed sort of Lagrangian backward error analysis techniques to then ask yourself whether this is related to some continuous Lagrangian systems.
Do xi and yi need to have the same dimensionality?
Not. I mean, there is a certain asymmetry between the two, right? Because you know the xi's oftentimes are some sort of analytical expression for a probability distribution. It's represented in terms of shape functions, and then the yi's can just be sort of discrete measurements, right? So they don't really have to live in the same space, if you will.
So the xi here don't need to be like point estimates. You could consider putting a
Yeah, you could put a smooth sort of distribution and something involved there. Yeah.
But how is possible that both x and y appears as the second argument in both of these if they are
Because you can still yes, that's a good question. Because you can still evaluate the xi's at points, right? So there's still some sort of measurement, if you will, which is implicit. So as an example, you could have a situation where you compute derivatives on the first slot, but then you don't have access to maybe derivatives in the second slot. You just have point measurements. So you don't have to treat the two things on an equal footing. You construct this just gives you a bit more flexibility.
But why do the d's need to be the same?
They don't have to.
You see, I mean, I can.
So I think that addresses sort of a more basic question, which is how do you choose D, right? And in the problem.
Yes.
And that is a good question.
Because often I think in some
Yeah.
problems the d between x and y is likely going to be different and driven by the
Yeah, it could be different.
the problem.
Right. Yeah. So it doesn't have to be the same. At the same time, it's like it's not always so clear how you choose the D in the first place. I'm not sure that there's really a very sort of systematic approach to choosing the D. I mean, it's like this sort of inverse problem. It's like where you choose the D by choosing the metric and the connections. That's sort of part of this process of, you know, engineering. It's like the divergence function with some sort of rationality in mind. Okay, but even that, it's like, you know, that's still not so clear, right? I mean, it's like how, okay, so maybe it's natural how I choose the metric. It may not be so clear how I choose the connection. Okay, anyway, so but yeah, a priori, there's no reason why they have to be the same D, and I'm not saying that they have to be, but this is one possibility.
You could think about a double pendulum where you only have one measurement, for example. Then I suppose it's a mismatch in X and Y. Or is that wrong?
No, because again, you can, I mean, you have, you know, so there's a sense in which one of them has more complete information. You can just subsample that. You can just evaluate part of it. You can look at marginals. You can do a lot of things.
Is it not the case that sometimes, at least, I think I've seen some kind of Bayesian algorithms where your data would enter into the fact that it's going to change the matrix. So I would see each time I add data to the system, I define D, but rather my
Sure.
xi and xi plus 1, the flow will be on probability distributions on the parameters of the.
Yeah. So I think in those situations, again, it's better to think of the update to the metric as being part of the distribution, as opposed to being part of the metric itself. I mean, it doesn't handle all possible sets. I'm not saying every single learning algorithm fits into this category.
Something.
Yeah. So okay. So anyway, it's so there's a student of a student at TU, it's like Berlin, it's like who's developed sort of these Lagrangian backward error analysis techniques. And so in principle, it's like one could apply it's like these things to such a problem in order to think of at least a class of machine learning algorithms as continuous time dynamic. Okay, so so let me now it's like then connect this to optimization. Okay. So of course it's like again it's like there's this sort of very close analogy between optimization and learning. Oftentimes possible to cost an optimization problem, so learning problem. Conversely, it's possible to cost learning problems and optimization problem. So, so if you have an optimization problem, says find a minimizer, it's like respect of some convex functional, it's like in a convex domain, and there's this work due to Nesterov, which introduced the following accelerated gradient descent method. It's not descent method, it's accelerated gradient method. So it's not descent method in the sense that the cost function evaluated along the sequence, it's like this not monotone, monotonically decreasing. But in any case, it's like what happens is that you can show that the convergence rate scales like big O of 1 over k squared, where k is the iteration.
But Melvin, isn't it typical that these functions are extremely non-convex?
Yes, it is. Then there's a whole problem of how you regularize it. It's like there's a lot of these sort of subsampling techniques. So it has to do with the fact that a lot of times it's like they're very, basically the data is very noisy, right? So you have to somehow do some sort of averaging. It's like in order to regularize the noise out of the problem. But yeah, it's like in practice, it's like these are extremely not smooth, not convex things. But they're in extremely high dimensions. So being extremely high dimensions also means that you tend to avoid it's like anything larger than like 1 saddles in practice. Yeah. So there's some advantages. It's like with working high dimensions, which you know it's like yeah. But anyway, so this is just to sort of connect it with accelerated optimization, and it's like give you a mechanical interpretation of this. So all right. So Nesterov showed that you know this 1 over k squared it's a rate that's optimal for methods which only use information about the gradient of f at these consecutive iterants, and that standard gradient descent methods only achieve convergence rate of 1 over k. So so there's a paper by Su, Boyd, and Candace. It's like which proved that the Nesterov scheme has a continuous limit which is given by this thing. So this is really sort of just a second order, it's like differential equation, it's like with potential like term, it's like, and then a damping term here. And one has to be careful by the choice of time step. There's an expression for it. So what's interesting about this, of course, is that it's a damped system. Okay? So this is sort of maybe not so inconsistent with what you expect. It's like, one way perhaps of trying to find a minimizer of a function is to imagine having some sort of particle, it's like in a potential, it's like having it roll down the potential surface, and you want to damp it so that it doesn't keep sort of oscillating around the minimizer. So morally, it's like there's perhaps some sort of mechanical interpretation. All right. So what's perhaps surprising is that there was a result, it's like due to Michael Jordan's group at Berkeley, which says that there is a Lagrangian and Hamiltonian interpretation of these things, which generalizes these results. The way you can generalize this is to, again, it's like have this Bregman divergence, and then when x and y are close, it's like this approximates what's called a Hessian metric. And then given this Bregman divergence, you have a Bregman Lagrangian and Bregman Hamiltonian. So let's think about it for a second. It's like you have a dissipative system. It's like when you have the Hamiltonian and Lagrangian formulation for this. And so what's missing, right? What's missing is that these Lagrangian Hamiltonians are time dependent. So it's like the Lagrangian Hamiltonian being time independent, and what give you the Hamiltonian as the Nova quantity. It's like these are time dependent. There's no assumption that the energy is preserved. Okay? So and again, morally, it's like there is some similarity. It's like between what I had presented before. It's like and what you see here. You have a divergence function which involves distance between a pair of points. So this is something like a divergence function being used to construct an approximation of the kinetic energy. And then explicitly, you have the cost function over here. This is just the function to be minimized serves as the potential energy. Okay? So this is very, very similar, if you will. It's like to sort of this divergence function as a discrete Lagrangian, and it's like approach which I described.
So what you could introduce a new time variable and make this an autonomous
Sure,
system
that's
again
one
with
good
kind of a weird new Hamiltonian,
That's what we do.
which you
Yes.
may or may not like.
Next page.
All right.
Can you,
Okay, maybe page after that.
can you finish within 5 minutes or so?
Sure.
I think,
Yeah. Okay. So, all right. 5 minutes. Okay. So anyway, okay. So the upshot, if you will, is that so there are these bunch of parameters, alpha, beta, gamma in it. If you choose them in a particular way, then what happens is the Lagrange flow of that continuous dynamic system converges the optimum value of 1 over t to the p, which means that unlike the discrete time case where you're limited to essentially p equals to 2, there is no limit on the rate of convergence of continuous time flow. So the question then is, it's like, why is it that in continuous time you can do this, but in discrete time you can't? There's this Lestrade theorem says that there's a limit, and does it have to do with certain approximation properties? Does it have to do with sort of what is called the oracle class of techniques you develop? Maybe you can't approximate this flow accurately enough within the given oracle class of algorithms. All right. To your question about, well, how do you go about discretizing it? Because of these scaling factors, the Lagrangian Hamiltonian are time dependent. And of course, if you naively apply a symplectic or variational integrator to such time-dependent systems, you oftentimes get very, very poorly derived results. So what you do instead, which is quite common in the context of time-adaptive methods, is you construct a new Hamiltonian, which is given by the Poincare transformation. Right? So you have a relationship between proper time and some fictitious time. It's like via some scaling parameter, you should use a new Hamiltonian, which is given as follows. Then you can show that you have the corresponding Hamilton's equations and sort of evolution equations before. And the problem, if you will, it's like with this Poincare transform Hamiltonian is that it's degenerate. So the Legendre transform is not reversible. But that turns out to be okay. So this is a degenerate Hamiltonian here. And so in order to go to extended phase space, which is what you need in order to make the problem autonomous, you basically set this scaling function g to be identically 1. Okay? So you get a degenerate Hamiltonian for which no Lagrangian analog exists. But they are what are called Hamiltonian variational integrators, and so it turns out that you can apply it's like this class of Hamiltonian variational integrators to problem, and then in particular there's an analog this variational error analysis result which still holds so long as this determinate condition is satisfied, and in particular it holds for non-degenerate Hamiltonians. So if the original problem is non-degenerate, the original time-dependent Hamiltonian is non-degenerate, and you have these p-independent monitor functions, which are the scaling functions, then everything is okay. Right? So in particular, it's like everything. It's like when applied to this Bregman Hamiltonian, this time rescaled Bregman Hamiltonian will follow true. So I'm running woefully short of time. Let me just sort of quickly summarize how you construct these sort of Hamiltonian variational integrators. So the basic idea is that if you have a Lagrangian system and a Hamiltonian system, and you had hyperregularity, which is it's like then you would have the usual Legendre transforms connecting the two, and then you would have going from Lagrangian to discrete Lagrangian, you have the usual theory. So what you really want to do is that you want to make this diagram commute, but you want this construction, which is the dotted line, to work even when you no longer have access to the Lagrangians. So the way you do this is you start with the exact discrete Lagrangian, you write down the Lagrangian in terms of the Hamiltonian using the Legendre transform, right? So L here becomes replaced with P Q dot minus H, and then you have to do a Legendre transform. It's like to go to either type 2 or type 3 generating functions, and then you get this expression. This is the object which you have to discretize to construct your discrete variational integrator. And let me just say why it is that you have to have type 2 and type 3 generating functions. So this is the toy example. If you have Hamiltonian which is given by QP, so this is a real toy problem, then you can check that the Legendre transform is given by this, which is clearly non-invertible. You lost all information about momentum. But more importantly, the associated Lagrangian is identically so. So even if you pretended that there was a type 1 generating function for this, right? What you would have to do is that you would have solved this Lagrange boundary value problem. Okay? And in particular, you have to specify the initial point and the final point. The exact solutions of this involve exponentials in time. So if you fix the time step, you cannot specify both the initial and final time. There's just no solution in general. So the point, if you will, is that it's not possible for you to always construct type 1 generating functions of degenerate Lagrangian Hamiltonian systems. So you have to go to these type 2 and type 3. So anyway, so let me sort of skip all of this and say the following, that information geometry provides a differential geometric interpretation of a class of machine learning algorithms, and in particular, there's this object known as the convergence function, which induces differential geometric objects like the metric and connection on spaces of physical manifolds, and we've related it to discrete Lagrangians and discrete mechanics. Okay, so there's this nice connection between mechanics and learning, and you can view machine learning optimization algorithms as being related to discrete mechanical systems. It's like on the space of Harmonic distributions. And if you apply things like backward array analysis, one can hope to construct continuous time analogs of machine learning algorithms. And then once you have these continuous time analogs, you can bring to bear all the tools we've developed as like geometric integration to construct now new classes of machine learning algorithms in this group.
Perhaps you should do most of the discussion while we're having cake, but maybe we can have a follow-up question.
Well, then I go. I don't need to. So for the autonomous Hamiltonian variational system, if you want to look at the time step, you do a linear stability analysis, and it usually, not always, it reduces to basically a set of coupled oscillators. You decouple and you can figure out your time step. But with this non-autonomous case, that doesn't work. So what do you do?
Yeah, I mean, it's.
I didn't know what to
Yeah,
do. We just tried, but I was like, nope, what do we do?
That's not so clear, yeah. So I'm not sure it's like what you would do. Yeah,
Okay.
so to be honest, we haven't tried. We had primarily been focused on trying to do the problem on the groups. We wanted to do sort of the optimization problem on the groups, and it didn't work so well, honestly. And we're still trying to figure that out.
So we have used those integrators to discretized water waveforms where you have a forced, say, piston type, and that's
Sure.
of course given in time, and that makes it non-autonomous. And that works well, actually.
Right. Yeah.
But maybe the problem is simpler, I don't know. But that
Sure,
works
but yeah,
well.
I mean, well, I mean, I think the Bregman Hamiltonian system is a bit subtle because it has these diverging coefficients which you have to deal with, so you have to be a bit careful.
All right, let's thank you